hasn't started.
Okay, now we are on air.
Okay, perfect. Hello everyone. So today we have David with us, and David is a fourth-year PhD student at Columbia, working with Daniel Rousseau, and so obviously he's interested in like sequential decision making, with a focus on policy evaluation. He also did his master's at Columbia University, and before that he was studying in France at École Polytechnique. So thank you, David, for accepting the invitation, and you can get started.
Well, thanks a lot for having me. I'm very happy to be here and presenting my work. So that we call the limited representational power of value function and its links to statistical inefficiency, which is joint work with my advisor, Dan Rousseau. And so that if you have a kind of like flash, maybe the article that we have put on archive about a year ago, there's been some kind of like major updates to it, and we're going to push a kind of like updated version soon. And this talk is reflecting this. So hopefully there's going to be kind of like, even if you're a bit familiar with the article, you may learn kind of like new things here. So just to kind of like ground the problem, even though it's like something I'm sure we're kind of like all familiar with, here is like, this is kind of the typical policy optimization cycle when you're facing kind of like an RL problem, or more generally a data-driven decision-making process. You usually kind of like pick an initial policy, you run it for a few epochs, you use the data that you collected to evaluate your policy, and then once you have a good evaluation of your of the policy that you've been running, then you use that knowledge about the policy to update it, and hopefully in a direction that improves. And then that new policy, you run it again for a bunch of epochs, you evaluate it again, and you continually loop the cycle until you converge to something you're happy with. Today, we're really going to be focusing just on the evaluation part. So we're not going to be caring at all about the update part. So we're just going to be fixing a policy, assume that it has been run for a bunch of epochs and we've collected data from that policy. And our goal is going to be to evaluate as efficiently as possible the policy that kind of like on policy evaluation. So the policy that we've been running, we're going to use those samples to evaluate that policy. Kind of like to flash just like the importance of this task within the whole process. This is just like a typical gradient policy update that I've just stolen from the seminal Sutton and Bartow reinforcement learning book. And you can see that these V hats appear, which are estimates of the value function, and having kind of like accurate estimation of those parameters are going to lead to better update of your policy. So this is really a central piece within that policy optimization cycle. So to ground kind of like the setting in which we're going to be working in today, we're going to assume that data is generated from a Markov reward process. So I'm going to be referring as those Markov reward process as the model or the models throughout the talk. And so this is roughly kind of like the classical MDP that we're all used to, but because we're fixing a policy, we can kind of abstract away the action. So here I don't have an action space. Like in an MDP, I have a state space, transition kernel P, a reward kernel R, an initial distribution, and a discount factor. But I do not have an action space because I have fixed a policy, so I can abstract away the action. This is kind of like the typical setting for studying policy evaluation. The goal is going to be to evaluate the value function. So for a given model, the value function that we're considering here is the expected sum of discounted reward given an initial state. And the way we're going to try to estimate that value function is given a data set of transition. Okay, so each data point, each xi in my data set is going to be a tuple where the first state is kind of like the current state. The first element of the tuple is the current state. The second element is the reward I collect at that state. And the third element is the successor state. So traditionally, we can study kind of like different way of kind of like the efficiency of different algorithms under different way of generating the data. The more classical one would be generated from trajectories. So you kind of like generate a full trajectory, and then you break that trajectory into those tuple transitions. Another way of viewing it is to think of those as being drawn like IID. So the initial state is drawn IID from some distribution that you can think of as being kind of like the discounted occupancy measure, or kind of like some kind of like stationary distribution. And then the reward and the next state are still drawn from kind of the law of the Markov chain. In this work, we study the IID case that I just presented, I do not think that it has like a major impact on the flavor of our result, mostly because our results are going to be asymptotic. And so kind of like in the large data regime, whether you have Markovian data or IID kind of like feels a bit the same because your Markovian data kind of reach some stationary point. And so it looks kind of like IID in that regime. So we'll be using kind of like tools from classical statistics, which have been developed for IID case. And that's why we opted for the IID setting. But yeah, I don't think this is like a major driving of our result. And again, we do not have any action because we fix a policy and we abstract away the action. So to put that work into kind of like the bigger picture of kind of like that I've been trying to pursue a bit during my PhD, it's a quest to understand value function estimation. And so I want to kind of put like different methods of value function estimation on a spectrum of more explicit modeling. So kind of like on the very left end of that spectrum, you have like direct methods like Monte Carlo, like supervised learning methods, which really use kind of like no modeling assumption of the system. It doesn't even require the system to be Markovian to work, and is really kind of like the simplest thing you can do, and it assumes like nothing about the system. Then maybe further on that spectrum, you have temporal difference. Temporal difference will kind of leverage the Markovian structure, but that's pretty much it. And then kind of like on the far end of that spectrum, you have model-based. Model-based really try to model everything about the world, about the environment, and leverage that to do policy evaluation. And so kind of like in our previous paper that was on the statistical benefits of temporal difference learning, we kind of explored that first part of the spectrum, which is what's the advantage of using those TD-like methods compared to using Monte Carlo, kind of like describing how the underlying Markov structure impacts the difference in performance between TD and Monte Carlo, and some like other advantages in like comparing the value at different states and stuff like that. And so this work is going to be the other part of the spectrum, which is going from methods like TD to fully model-based. What is kind of like the difference between those methods, and what kind of statistical performance difference does it lead to? And so as I kind of like just hinted toward, we're going to try and explore a very well-known dilemma in the RL community, which is choosing between two paradigms for value function estimation. I mean, it's two paradigms for RL in general, but we're going to explore it in the case of value function estimation. So the first one is model-based. And so this is kind of like a general picture of what I have in mind when I say model-based. It's obviously not a formal definition, but it's kind of like you're going to try and model the world, the dynamics of the world. And using those dynamics and the data that you've collected, you can come up with some kind of generative model, and you can use that generative model to output an estimate of the value function. So, if you're like in a simple case, like a tabular case, maybe you can like learn an estimate of the model and then actually use some math to transform that into a v-hat. But if you're in a complex world, maybe you actually learn a generative model of the world, and you use that to sample from that generative model to then like compute some v-hat. And on the other hand of the spectrum, you have those model-free methods. So those, instead of modeling everything about the world, try to model just the thing you care about, which is the value function. And using the same data, try to come up with an estimate. And so kind of like the folklore in the community is that model-free methods tend to be easier to implement because they don't have to estimate like or learn that super complicated object that can be the dynamics of the model. They're typically more like computationally efficient. They also tend to be more robust to misspecification, but they tend also to be statistically inefficient compared to model-based methods. And so there's a lot of work kind of like trying to see whether, given how positive the two bullet points are, can we kind of improve on the third? And so this is what we're going to be investigating in this work. And so this work is going to be purely from a statistical point of view and not at all from a computational point of view. The first thing is I kind of want to challenge the name kind of like model-free. Model-free hints as like there's no modeling happening. But what does it really mean to be model-free? So this is a quote I stole from that paper, A Tour of Reinforcement Learning, the view from continuous control from Ben Recht, which was saying that choosing a parameterization of the Q function, so the value function for us, is a modeling assumption. The term model-free almost always means no model of the state transition when casually claimed in the reinforcement learning research. And so I think to some extent, this quote points to something kind of deep, which is that the idea of model-free methods is very natural. Model-free methods try to capture that natural idea that we should model the simple object we care about and not model all the complex aspects of the environment that might be extraneous to our decision-making problem, right? If I only care about the value function, why would I model anything else? And so our research question is going to be, when is there a gap in statistical performance between modeling the value function compared to modeling the transition? So we only consider the case where modeling is correct. So when I'm going to be comparing some model-based methods versus some model-free methods, I'm going to assume that the assumption made in the model-based methods are well specified, and the same in the model-free methods, that my assumption about the value functions are correct as well. And again, since we are interested in statistical properties, we are not going to be thinking about how the estimator is computed. So we really are going to be interested in estimators in the kind of statistical sense that they are a function, a mathematical function that maps input to output, and not really dive into how that mapping is computed. And so what we do is that we offer what I hope is a natural definition of model-free methods in terms of modeling primaries rather than algorithmic procedures. We will show that model-free methods are implicitly operating on an induced class of models. So although it seems like we're working like on a class of value functions, we are actually implicitly kind of working on some class of models, and I'm going to tell you what that class of model is. And we'll use that to kind of explain some puzzling examples where model-free are sometimes efficient and in other cases inefficient. So I'll show you some examples. And in those examples that are gonna come, I'm gonna be comparing two methods. On the model-based side, I'm gonna be comparing the plugin estimator. So I'm gonna have some modeling of the transitions, and using that modeling of the transition, I can run a maximum likelihood estimator of the model. And then I can output the value function associated with that estimator. So I act like my estimated maximum likelihood estimator is the true model, and that's my value function. This is kind of like a very natural model-based thing to do. And on the model-free side, I'm doing kind of like the main model-free algorithm we have in RL, which is LSTD, which just try to find a value function that solves a fixed point of the potentially projected Bellman equation. So let's dive into the examples. So the first one is just the tabular case. So everything's finite. We don't really have any structure. And so if I generate a random model and I plot the performance of plugin and LSTD on there, we can see that they overlap perfectly. And so this is probably no surprise to like most people in the room, because it is pretty well known that for tabular models, TD and plugin are the exact same thing. Right? Mathematically, they're the same estimator, the same function. So obviously, there's no gap in this case. Now, staying in the case where we have finite state space, let me show you another example where there's some structure.
Oh, wait, just one quick question.
Yes.
How do you actually define the norm when you write like MSE on the left-hand side?
I think this one is unweighted. So just like for every state.
Okay.
Yeah. So I think for some of the, okay, so in this case, because they're exactly the same, like no matter what norm you find you used, it's going to be kind of like they're going to be overlapping.
Yeah, I agree. I just feel like, okay.
Yeah.
It seems like a more
other
important
examples
consideration when you go beyond like tabular.
Yeah, in some other examples, I've tried sometimes like changing a bit, whether I do kind of like I use kind of like an online or an offline weighted, kind of like whether I weight by the occupancy measure or not.
Yeah.
And kind of like when there's a gap in both cases.
Yeah, that makes sense.
There's no gap.
Yeah, I mean, weighting by the occupancy measure seems like you kind of have to do something like that if you're in a non-tabular setting, right? Yeah.
Yeah,
I mean, I guess you can be in a tabular setting and still like apply you know, whatever non-tabular like function approximation, but I'm just saying like most settings where there would be like a point in applying function approximation to begin with, you imagine that the number of states is large enough that you don't want to use like unweighted. But anyway, we can move on.
We're going to be mostly, I'm actually going to be exclusively also talking about kind of like parametric families.
Yeah.
So usually the norm I use is kind of like the norm on the parameters.
Yeah, for sure. Although even that one, I think it's still probably natural to weight by like, you know, whatever, like second moment of the features or something like this, but yeah.
So my second example, which is still with finite state space, is going to be factored MRPs. So imagine your state as being like a d-dimensional vector, and each component of the state evolves independently. So S1, like the first component of the state, evolves independently of the second one, and so on. And for each coordinate, you collect an independent reward, right? And then to get the total reward, you sum all of those independent rewards. And so that defines a transition over the states. So kind of like reading in math, our state space is the product state space of like where each of the components leave. The transition kernel is just the product of the independent transition kernel, and the reward is just the sum of the independent rewards, right? So if we have that structure, what can I say about my value function? I know it's separable. So I'm saying that the value function can be written as a sum of value function on each component. This is a pretty common assumption in a lot of practical settings. So I highlighted two works. The first one is like an application of RL in Lyft, where they kind of have a system with a lot of agents and they view the value of the whole system as kind of like a sum of value on each agent independently. And the second one is kind of like doing the same kind of philosophy, but for healthcare interventions. So now let's see if I run kind of like plugin. So I try to estimate my different PIs and RI and do the plugin estimator versus if I run LSTD on those separable value function. What do I get? So here you can see that LSTD is doing much worse, right? I'm plotting the error, so the lower the better on the graph. So plugin is kind of like nearly staying at 0, and LSTD is kind of going through the roof. Okay, so this is a case where for factored MRP, there is a large gap between LSTD and plugin. Okay, so we're still in the case with like finite state space, but I've added structure. I've added structure to the transitions. But importantly, this structure in the transition was also reflected in structure in the value function. So it's not like I have structure on one side, but not on the other. So it's kind of like a fair comparison, I think. Yeah.
Oh, wait, just quick question. Okay. Maybe you said this already, in which case I apologize. But are you keeping the number of like samples fixed as you increase the dimension D here?
Yes.
Okay, cool.
Yeah, I think that's why the numbers are high.
Yeah, for sure. That makes sense.
I think the importance is that kind of like there is a gap between those two methods, and like I'm using the same number of samples for both methods, so this is a fair comparison. So now let's move to the continuous setting. So my state lives in RD, and my transitions are linear. So this is kind of like an autoregressive model. So my state, my successor state is just a linear function of my current state plus some noise, and my reward is just a linear function of my state plus some noise. And so if I have this structure, what I can know about my value function is that it is linear in the state. And so now again, I plot a plugin versus LSTD. And again, they overlap perfectly. And actually, again, like in the tabular case, we can prove that for these models, those two algorithms are actually mathematically the same. And now let me do another small twist to that model where I change the reward to be quadratic instead of linear. So this problem is known as linear quadratic control. And this is actually an example of that we borrow from that 2in-Rect paper that I'm going to come back to in a second. So when you have changed that reward to be quadratic, then the value is also a quadratic function plus that constant term. And so if I do the same plot, then we have a big gap again. And what that 2in-Rect paper does is they actually kind of like compute the performance of plugin and LSTD, both in the policy evaluation and the policy optimization case, and they show that there is a provable gap. Right, and they kind of raise the question like, okay, why is that? Is it inherent to model free versus model based? And we hope to like bring some clarity to that. But kind of like to sum up like the overall picture, is like we have those two examples where they're kind of related, but in one there's no gap, and in the other there's a large gap. And so that kind of raised the question of, did I just pick the wrong algorithm? Maybe like in those cases where I have a large gap, is it just LSTD sucks? Or is there kind of like a broader problem with model-free methods in those situations? So to be able to like kind of like go on and give you some results, I first need to tell you what I consider to be a model-free method. So just to first start by reviewing kind of like some attempts at defining model-free methods, there's a definition in 2006 by Strail. I'm not sure how to pronounce. Sorry if I butchered that. And this suggests a computational definition where they are in the tabular case, like in an empty piece with actions, and they consider that a method is model-free if it uses kind of like significantly less space complexity than S squared to the S square A. So S square A is how much memory you would need to represent the full transition matrix in the tabular case. So they say, okay, if you're like asymptotically using less than that in space, then you cannot be storing the whole model. So we're going to say your model free. So this doesn't capture a nice like computational. Yeah.
Yeah. So yeah, before we go into this a little bit, a question regarding the robustness of the results of the previous slides. So you chose these specific metrics, and Dylan was already asking questions about that. Have you tried any other metrics like L1, L infinity, whatnot? Like, what do we know about how sensitive these results are to the metric that you chose to measure how well the value function is estimated?
So kind of like, you mean like what norm I use to?
Yeah. You could change it to anything else, and would it change the results? Like, is this really the right norm?
So again, so I've tried something like that as testing like some different weighting the states by different
but it's still L2.
And there's still a gap, and the result we have actually kind of holds for any convex bowl shape loss.
Okay. So that will be
cool.
L1 is going to be included in that sort of bowl shaped. How much is a bowl L1?
Yeah, I'm not sure.
Yeah.
Oh,
okay.
yeah. Wait. Yeah. So when you said convex ball shaped loss, I was just assuming like, just like you like pick some convex set and you do like the usual kind of like norm induced by that convex set, right? Is that what you mean, or is it more specific than that?
I think it's more specific than that.
Oh, okay.
I think we state
we'll see.
We state all of our result in that kind of norm.
Yeah, sounds good. Okay, yeah, maybe we should just let you get to say what the actual.
Oh yeah. Yeah, absolutely.
That's good.
Exactly.
So yeah, trying to kind of like review the landscape of what definition we've had for model free. So there's this definition that is a computational definition of model free methods. And so as we've seen in the example, we have cases where like you can compute the same mathematical function a few different ways. Some might be considered model free by this method, some other wouldn't. So this is not really adapted to the question we're asking, which is from a statistical standpoint. More closely related, there's this paper from Sun et al. In 2019 that tried to come up with like a more statistical definition of model free. And what they define to be a model free method is a method that never kind of like has access to the state, but only view the states through the different possible value function of that state. And so again, so in that setting, they managed to kind of like get some exponential gap between model free and model based methods. And so it definitely captures something very interesting about some aspect of being model free. But if V is expressive enough, if the class of value function you're using is expressive enough, like linear functions like we used before, well, if you know the image of your state by all those functions, you can recover S exactly. And then there's no more distinction between what is model free, what isn't. And so this is not something that we can use to explain kind of like the puzzling examples we saw earlier. And so one thing I want to say before I come up with my definition of model free is I'm not trying to come up with like the right exact definition of model free that we're all going to agree on, but I'm trying to capture something about what we mean when we say model free that can explain the examples I showed you earlier. So I think those two methods definitely capture something about model free, and it enables to explain something we see happen in some examples. And I'm going to try and capture something else that explains something else. So to give some intuition about what I mean about a model free method, let's take this famous Tetris example. Maybe I want to do a function approximation. And so I want to model my value function as a linear function of some features of the problem. Could be like the column heights, the intercolumn height differences, etc. And so I kind of like get those features. I say, I think my value function is linear to those features, and I kind of forget about everything else about the problem that I kind of deem irrelevant to my value function once I have, say, okay, those are my value functions. And then I can fit the best linear function in that class using kind of like whatever algorithm I want, like LSTD, etc. And so to kind of like put it like graphically, I start from some problems of interest. And so I kind of purposely put two types of problem, like factored problems where I can describe you in math exactly like what the problem where this is a problem where, you know, I could actually do model-based pretty easily. And some more like unstructured problem like Tetris, where, you know, I don't really know exactly how I would model the transitions. But in either case, I kind of like translate what I know about the problem into value function. So that's what I mean by modeling in value space. I model what I know about the value function of the problem. And once I have those value functions, I kind of forget about my initial problems, and I just work within that class of value functions. So now let me make an attempt at making like a definition. And before kind of having like a very general definition, I'm going to try and generalize LSTD. Hopefully, we all agree that by whatever definition of model free you have, LSTD is model free. And so I think a good way to start is, can we come up with a generalization of LSTD that we can call model free? And so I want, like the way I view LSTD is that it roughly tries to solve the Bellman equation, right? Like all those LSTD methods kind of do something of that sort. And so the two kind of like important features of that problem is that it is solving a fixed point equation, and the true value function is the only solution of that fixed point equation. Right? If I have kind of like those two features, to me, it's an algorithm that looks like LSTD and that does value function estimation, right? So the first bullet point is I look like LSTD, and the second bullet point is I'm solving the value function estimation problem. So in practice, we don't know the model, so we can't solve like the true fixed point equation, but instead we can solve the empirical version of that equation, and those are called in the statistical literature M estimators. So we call an M estimator any estimator that is a solution in our class of value function of an equation, a fixed point equation of that sort. And what do I mean when I say that it's a model-free estimator? It kind of has to work for all value function in my set, right? As soon as a problem has a value function in my set of, in my class of candidate value functions, my algorithm should work properly. That's kind of what LSTD is doing. And so my definition of a model-free M estimator is an M estimator that for all M, such that the value function is in my value function class, V of M is the unique solution of that fixed point equation, right? So if my function psi verify this condition plus some smoothness condition for kind of like statistical analysis, then it's going to converge to the right thing whenever the model is well specified. And so now that I have given you kind of like a mathematical definition of what I consider a model-free M estimator for now, I can tell you my result. So to start, I'm going to call this set of model that have their value function in my class of candidate value function. I'm going to call those models consistent with my class, my candidate class of value function. And now the theorem is just the performance of any model-free algorithm is going to be lower bounded by the performance of the plugin estimator on that class of all model consistent with V. Okay, so I'll show you a picture and I'll come back to the theorem. But basically, the picture is we start from some problems of interest. We kind of like try and code what we know about the problem in the value function. But there's actually a bigger set of models potentially that have the same class of value function. And our model-free methods are actually operating on that bigger class of model. And so here I put that like that bigger class of model is kind of like those models consistent, but I also write it's equal to kind of like interrogation mark. And this is to highlight that in practice, I kind of know what my problem of interest is. I don't necessarily kind of like super know what that bigger class of model is. It exists, but it's not necessarily very easy to characterize, and you might not even be aware that it exists. You might feel like, there's kind of like a one-to-one mapping, or like. And so let me just to kind of reflash now that the theorem that we've seen the performance, this is saying that when you specify a small set candidate set V, the model-free methods are implicitly competing against a possibly large class of models. Yeah.
Oh, yeah. I just had a quick question. How do you actually define M hat for this theorem?
It's the maximum likelihood estimator.
Oh, yeah. But is it like, I guess, maximum likelihood over this set script M of V?
Yeah,
or
yeah.
like,
Yes,
I see.
it's the maximum likelihood in that big set of model.
Interesting.
Yeah, this is a key point. Yeah. So you're doing maximum likelihood in that big class of model instead of like what you would do ideally is a maximum likelihood in that small class of model.
Yeah, for sure. That makes sense. Okay, cool.
So let me show you now like a toy example to kind of like illustrate that result. So I'm going to take my example of like linear autoregressive model. So my transitions are linear, my reward are linear, but compared to before, I am going to assume that my transitions are diagonal. And so the first thing I want to do is to know, okay, what are the value function of such a system? So if my system has this shape, the value function is going to be linear. And so now I'll show you a plot like I did before of the performance of LSTD and plugin. And again, we have like a very large gap between LSTD and plugin. And so, I mean, as you can guess, because I'm showing you this right after the theorem, what's happening is we're in this case. If you run LSTD on that linear class of linear value function, you're actually implicitly working on a bigger class of model. And what is that bigger class of model? Where it's convenient, I told you earlier, this is the class of all linear systems, where I just do not have to assume that diagonal assumption on the matrix. And again, we saw earlier that in that case, LSTD and plugin are equivalent. So in this case, it's not even that you're kind of like implicitly working in that bigger class of model. LSTD is actually kind of like explicitly working in that bigger class of model. So now that I've showed you that toy example, let me revisit the less toy example that I showed you at the beginning. So in the factored Markov reward process, can we find systems that are not factored that have separable value function? Well, now if I pick any kernel, transition kernel P, that does not have to be factored, and I correctly pick my reward function, the value function is going to be separable. Right? This is kind of like very simple math. I want I minus gamma P inverse R to be equal to some V that's decomposable. I just multiply on the other direction. That gives me the R that I need to pick. And how many such models there are? So if you fix kind of like each component to be able to take K values, there are order K squared D free parameters to parameterize factored MRPs. But the number of models that have separable value function is exponential in the dimension. That doesn't necessarily mean that the gap is going to be exponential, and I'm going to come back to that later. But I think it's already illuminating to realize that when you think you have actually encoded a lot of things in your separable value function, there's actually still a lot about your problem that is not encoded. Maybe even less toy example is LQR. In LQR, it's a bit harder to see what LSTD is doing. This is going to be more about LSTD specifically. So we said that when we have those quadratic rewards, the value function has this shape, kind of like roughly quadratic. And how do we run LSTD for this kind of problem? Well, we would like the value function to be linear. So what we do is we come up with a linear function in a higher dimensional space. We transform our value function by moving to a higher dimensional space such that the value function can be linear. So that S transpose LS, we can rewrite it as being the trace of SS transpose L. And so once we have that, we can rewrite our value function as a linear function, but this time, instead of living in RD, it's a linear function that lives in RD squared, right? Like our features is a matrix in D by D. So we now have a linear function, like the value is linear, but in that higher dimensional space. So what do we do now? We just transform our data set by mapping each of the state to those features. And then we can use LSTD in dimension D squared. But I told you earlier that LSTD is equal to plugin. It is the same mathematical object. So we can interpret what LSTD is doing in that case as trying to running a least square regression from RD squared to RD squared. So we try to explain the transition from phi of S to phi of S next as a linear mapping in R of D squared. And we can use symmetry to reduce the dimensional layer problem to kind of like D squared over 2, but that's kind of like that doesn't really contradict the main point. This is like you're still working like a much higher dimensional space. So I just said LSTD try to fit a linear transition and linear rewards for phi of S instead of S. But what does the true transitions and reward look like? So I wrote you what the transition looks in the feature space. So the feature space, the next state is kind of like this linear transition. So this is like in the space of matrix, this is a linear function plus a constant. And similarly, the reward is a linear function of the features plus a constant. And there are three things to notice here. The first is those transition and reward, they're affine, not linear. So LSTD is trying to fit a linear function to approximate those. When they're not linear, they're affine. The second thing is, this is kind of hidden because I showed you the expectation, but when you look at those transitions, the noise are not Gaussian IID anymore. The noise is actually state dependent. So OLS is not even the maximum likelihood in this case, because the noise aren't like IID Gaussians. And finally, the transition has ordered D squared free parameter, right? You just need to know that A to be able to like reconstruct the transition. But LSTD will search among all linear mapping from RD squared to RD squared, which is kind of like a D to the fourth free parameter space. And kind of like taking a step back of like this specific example, this process that we did in LSTD is actually pretty common in like machine learning in general. We're trying to estimate a pretty complex function of low dimensional parameter. Here, it's like the complex function is like a quadratic function. So instead, we start by transforming our states into high dimensional features to try and then learn a simple function. So although maybe like LQR is not like an example of like super interest to you, but the process that leads to like working that bigger class of model is actually relevant in many cases. Yep.
Oh, sorry. Actually, would it be possible to just go back to the main theorem? I just had a question about that.
Sure.
Statement of it. Sorry.
No worries.
Oh, I see. Okay, it's this holds uniformly for all M in the bigger class.
Yeah.
Okay, interesting. Okay, that's cool. So that's like very important, right? Because like for an example, right, like in the factored case, right, it's like you say you start with factored MDPs, you go to factored value functions. Now you end up with this bigger class of MDPs that are not necessarily factored. But to like kind of explain the performance you're seeing, you do still want it to be the case that like when you run it on an MDP, which like is fully factored, you are actually like paying for MLE on like the bigger class, which is not necessarily fully factored.
Exactly. Yeah.
Okay. Excellent. Nice. Thanks a lot.
Thanks for the clarification.
Yeah.
And so I think that's also kind of like maybe the point where there's some like practical insight to this is, really what I want is just an algorithm that works when the transition has this specific structure, like A phi A transpose. But I'm using an algorithm that's like broadly work for any linear function in RD square. So by using this like super broad algorithm, I'm gonna pay a statistical price. Like kind of like the only hope I have to be more statistically efficient is that my algorithm works when my transition has this shape and doesn't work when it doesn't have this shape. It's like this kind of like a no free lunch in some sense. And so kind of like to come back to like, so far my theorem was just for M estimators. So can we extend that past M estimators? So this is my definition of model free. So I want to say that an estimator is model free for a set of value function if for all model in that class, first my estimator converge at a root and rate. So that's kind of like what you would usually think of as it works. And I'm going to add this convergence happens locally uniformly. So to comment on this and in the next slide, what I mean by locally uniform convergence is kind of like a statistical concept that's called regularity. That's pretty well developed in the asymptotic stats literature. And just to flash you what it is just saying models that are undistinguishable given the data should be treated similarly. So this is saying if you have a model M and you perturb it by some delta over root n, as n goes to infinity, it should look like there was no perturbation. Because basically the only way you can kind of like detect this is by setting a threshold like delta, but then I can pick delta over 10 or delta over 100. And so kind of like those changes, if you were to try and test them, it's kind of like in the diagonal case versus non-diagonal case in the linear systems, I could try and do something like, first I try to guess whether my matrix is diagonal. If I think it is not diagonal, I'm going to run LSTD for non-diagonal matrices, plugin for non-diagonal matrices. And if I think it's diagonal, I'm going to run plugin for diagonal matrices. So this is kind of like forbidding this kind of like estimator that try to kind of like cheat in some sense. In practice, like any practical estimator you develop not trying to violate this would not violate this, or maybe would violate it in like 1 point, like Stein estimator. So this is not really core to the result, but just wanted to like be fully honest on what our theorem has. And so once you have the definition, like we have the exact same theorem for like any model free estimator that satisfy this condition. And our M estimator under kind of like the smoothness condition of psi, we're validating this like regularity condition. For the last piece of the talk, I want to kind of like I've been some sort of lying to you, you know, it's like, yes, we work in that bigger class of model, but why is that bad, right? If it maps to the same class of value function, why is it harder to work in that bigger class of model compared to like the smaller one? In other sense, it's like we lose information, sure, that's nearly tautological. But why is this information relevant for value function estimation? And so I'm going to make a connection to nuisance parameter. So the question we've been asking is, we have data that's generated from a complex model M, but for decision making, we only care about a much simpler object, the value function. And so to learn V from data, can we forget about elements of V that are extraneous that are extraneous to V? And kind of like an old statistical question is you have data that is drawn from a p theta, where theta is a possibly complex object. But for decision making, you only care about some f of theta. And so to learn f of theta, can you forget about anything about theta that is not f of theta? And so the statistical literature to kind of answer the question, try to break down theta into 2 parts. The first part, f of theta, is our parameter of interest. The second part is called the nuisance parameter. So this is everything that is not in theta, in f of theta, sorry, that you would need to be able to rebuild theta. So this is all information you don't really care about. So let me mention 2 examples of that. So if you're trying to estimate the mean of a normal distribution with unknown mean and unknown variance, the mean is obviously the parameter of interest, but the variance is a nuisance parameter. If you wanted to recreate the distribution, you need to know it, but you really only care about the mean of your distribution. Another example is you have kind of like, you have an intervention and you're trying to estimate the causal effect of that intervention. So maybe you observe some y that is composed of some alpha transpose x, so that's the effect of your intervention, and some beta transpose z, which is some user-specific outcome, like how the users interacts with your system. And so let's ask this question for those 2 examples. Is discarding extraneous information damageable? So when you're trying to estimate that mean of the normal distribution, you can just forget about, like, even if you know about the variance, you can just forget it. You can just run the sample average. It does not require knowing the variance, and this is asymptotically efficient. You cannot improve on that even if you knew the variance. Now, in our other example, if your treatment and your user features are correlated, and you lose some information on beta, you're going to lose statistical power. So there are cases where you can forget about extraneous information, and there are cases where you can't. And I think a lot of like kind of simple statistical problem, kind of like toy problems we can think of, usually tend to fall into the first category, that we can forget about extraneous parameter at no cost. And that's why it is maybe a bit unintuitive that in the value function case, we cannot. And so one necessary condition to be able to forget about the nuisance parameter is that the mutual information between the parameter of interest and the nuisance parameter is 0. The nuisance parameter has to be uninformative about your parameter of interest. And maybe kind of like, maybe where the core of the paper is in its examples, because it shows that in general, in reinforcement learning for value function estimation, there is no reason to believe that this mutual information is 0. So kind of like the main theorem I presented to you, in some sense, is like nearly tautological from the definition, but the important bit is that working on that big class of model for value function estimation is actually damageable. And so kind of like to conclude and like zoom out a bit, one thing I mentioned at the beginning is like in the folklore understanding of model-free methods is that they're more robust to misspecification, but statistically inefficient. And I think this helps kind of like understand a bit why this is happening, because model-free methods tends to kind of like implicitly underspecify in model space. So because you work implicitly in that big class of models, you have less chance of being misspecified. And the other thing is kind of like, can we model at a finer level of granularity? So this is something that's very popular right now in the RL community, is to do kind of like multitask or multi-goals learning. So instead of learning one problem, so for one reward function, you will learn multiple tasks at the same time, represented by multiple reward kernels. And so if you do that, then you're going to be working kind of like implicitly in the space of model, such that your value function falls into your class of value function, but for all tasks. So you work at the intersection, and that enables to kind of like reduce the size of the model space you work in without having to fully model the transitions. And in some cases, if you work on like enough tasks, you can reconstruct exactly the model. So in some cases, modeling a lot of tasks is going to recover just modeling the transition. And if you just work with a few tasks, then you're going to be somewhere in between. And so kind of to conclude and to recap, there are two very important bits to what I presented today. There's a loss of information when modeling directly the value function compared to modeling the transition and forgetting about information that seems extraneous to the value function estimation. And maybe the real core of this paper is to actually show examples where that extraneous information is actually informative of your value function, and forgetting has a statistical cost. And then that kind of like help explain a bit some of the phenomenon we see with model-free methods. So thank you very much.
Nice.
There is a question from the audience. Do you want to unmute yourself and ask?
Yeah, I do have a burning question. Do you actually have some examples where the empirical gap that you observe can be theoretically also proven? That should be possible, right? Like given the big gaps that you're seeing.
I mean, so basically in the theorem, I read it like this as like the plugin performance on the big class of model. So this is really the Kramer-Rarrell bound, right? Like, sure. And so this is something that we are planning to do before like publishing the new version of the paper is like for this example, we can just compute that grammar error lower bound and have kind of like a provable gap.
Okay.
That makes sense.
So that would mean that for LSTD, you would get a lower bound that somehow are separated from the quantity that you get from either grammar row or like whatever upper bound you will have for a model-based mental.
So basically, you can direction.
I guess for the examples, you could just compute the MLE over the bigger class here, right? Like,
yeah. Yeah. I mean, it's not necessarily easier than doing the math in some of those problems. Like in the
I guess I'm not sure what like dimension the examples were. Oh, okay. No, sorry. I guess you actually wrote it. You wrote the dimension. So okay.
Yeah, I think like sometimes like I don't know, in the separable value function case, the bigger class is like grows really, really fast.
Yeah. Fair.
But the if you were to look at the information matrix, it has like some nice like diagonal by block kind of structure, and you can maybe do the math more easily than the simulation. But yeah, basically to answer your question, Chaba, is like we can compute the grammar lower bound for this class of problem and for this class of problem. And we can show that if they're not the same, there is a gap. And so anything that's model free cannot do as well as someone that lives in that class, someone that knows that we live in that class of model and just do like plug into that class of model.
Well, assuming that you have models that reach the lower bound. Or like you,
okay, yeah. So the plugin estimator reaches the lower bound.
Yeah.
You should do MLE and you plug in, that reaches the lower bound. So
yeah. Okay. That's cool. Okay, and then back to the question of what metric you use. I guess given all this, you're kind of looking at asymptotic, I don't know, identifiability or something. So from that perspective, it doesn't really matter. Yeah. And I guess like if you have an like the argument is that if you have an asymptotic gap, then you will see a finite time gap as well. Like there's no.
Like in that kind of like example where you like in the nuisance parameter kind of like framework, sometimes like there are cases where not knowing the nuisance parameter, like for instance, let me take that example. That's like an example. If X and Z are not correlated, then you can just kind of like run OLS and at the end discard the beta part. And this is efficient. But now if you knew beta, you could actually subtract it and get better finite sample performance. And this is usually the way it works. Like if you knew the nuisance parameter, the gap gets even bigger in finite samples. So asymptotics is actually kind of like it's
indicative in this case of and even more of what happens with finite samples.
Interesting.
It's not completely automatic, but I believe it's true.
Yeah, no, it's not completely automatic, but
Yeah, I am kind of curious, like, what is actually hiding in the like O of 1 over n term in the main theorem?
Nothing. It's just kind of like a nicer way of writing it. It's just kind of like the result. So the result is kind of like the more general result is you can kind of like stripe the expectation in the norm and just look at the limiting distribution of root n v hat minus vm.
Yeah.
And you have that the variance, that anything like on the left, the limiting distribution is lower bounded by a normal.
Yeah.
0 Kramer lower bound for the variance.
Yeah.
And so this is just saying kind of like, instead of writing it as like n times limit of n times and
okay, maybe a better way of saying this is like, I'm curious like what happens when you go beyond like kind of all the standard like parametric like modeling assumptions and
I agree.
asymptotics is
that's
maybe a better way of saying
I see,
like
okay.
I would be interesting to understand that. Yeah,
that's a good question. I don't have a good answer, but that's a good
for
question.
sure.
I'm a little bit confused about the regularity assumption of where do you actually need it?
So this is for having really for all M, right? Because
like for developing the asymptotics, but yeah, I guess.
This is really, if you have a, like
right.
In the example where we have like diagonal, yeah, here. So there's something you could do is try and run a statistical test to, like you estimate your transition matrix and you run a statistical test.
Switch.
And you switch. And this is going to be very good on diagonal matrix and very good on non-diagonal matrix as well.
Yeah.
But this is not really something you'd want to do in practice, except like if you really know that there's no chance that, and this is having like really more information, right? This is
yeah, like, this part about like what people want to do
like
in practice are not at all, but yeah,
it's kind of like having an infinitely strong prior that if you're close to being diagonal, you have to be diagonal.
Yeah.
And so if people you don't exclude those kind of estimators, then there's no chance of writing a theorem. I can always kind of like pick one specific model,
right,
and be like, oh, if I'm close to that model, I'm going to give that value function. Otherwise, kind of like Hodge estimator, and then you have no chance of like writing anything interesting.
Yeah, I'm not entirely convinced that people will not venture to things like this in practice, or like whether this is really outside of the realm of possibilities when people would do something. I mean,
I fully agree with that. That's kind of what the disclaimer at the beginning of we are trying to capture something about model-free methods, but for instance, if someone was trying to do this, I think we can debate whether this is really model-free, because you start to model more kind of like finally what the underlying model is. So you're not modeling just what the value function is, you're actually modeling what you believe about the transitions.
Yeah.
And I agree that in practice, you might still want to call like some of those methods, you might still want to say they're model-free, you might not. And this is where I'm saying, okay, this is not like our definition of model-free and able to like say something. Yeah. That doesn't mean that like you don't want to do this in practice. Actually, it kind of says maybe you want to, even if you're not like explicitly computing a model, you might want to like, I don't know, regularize in some way to capture models. But I agree with you. That's not like irreasonable in practice.
Yeah, when you were talking about the M estimation, I was totally thinking about that. Well, how can I tweak this psi if I have some ideas about what a model could be, that like I write some imp soup, blah, 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 some really complicated thing. And there you go. You will have your model-based algorithm implemented as if it was model-free.
Exactly.
But
I think this is actually what I think one of the takeaways is actually, if you want to do something that's computationally efficient, but also statistically efficient, that is kind of maybe what you need to do. Like, try to write your algorithm in a way that doesn't need to explicitly compute the model, but that still implement in the way you compute it stuff you can model about the world.
Yeah. By the way, so the regularity assumptions are going to fail then for if I do this two-step thing of like, let's estimate a model and then let's estimate the value function?
Yeah, it fails. And it fails around a diagonal matrix, like whatever thing you use as like a singular point that you're testing is going to fail around, because depending on whether you approach your single point, like let's say you're testing whether the matrix is diagonal.
Yeah.
Whether you approach that point within the space of diagonal matrix or from outside the point of diagonal matrix, you're going to have different.
But if I have a model-based algorithm, it's not going to do the testing. It's going to do the model estimation. So the model estimation part could be smooth, regular, whatnot. And if I compose regular things, it's like which part is not smooth, or which part makes it not regular. Like, I'm really puzzled by this now.
So sorry, can you re-explain?
Yeah, so I was thinking that, okay, maybe I'm misunderstanding everything, but I was thinking that the model-based approach would work by estimating a model. Yeah. And I normally, like you do maximum likelihood, something like that, it's going to be regular. So that part is kind of smooth, nice.
Yeah.
And then on the top of it, I solve the model for the value function. So that part is usually smooth in the model parameters. So it's like, I don't see how the non-smoothness for the model-based method would arise. Or like, what rules out the model-based approach that first estimates the model and then uses the estimated model to come up with a value function as a model-free approach.
So
like it's regular, right? Like this thing is regular. So it's like what is that is not met?
Delta is actually a vector here, right? It's like a perturbation. And so the definition of regularity depends of like in what space you want to be regular.
Yeah.
So like taking that picture, model base is definitely regular within that like green. Like if you only allow perturbation that stay within the green space, you are regular. But then if you allow perturbation that exit the green space into the blue space, you're not regular anymore. Like if you are doing plugin for diagonal matrices, this is regular among the set of models that are diagonal, but it's not regular for all linear models.
I see.
Or no, sorry, no, actually, if you do plugin, it is regular, but it violates the other condition. Like if you just estimate. I see. Okay, something that I've missed in the definition. That thing that convergent distribution has to be like a zero mean distribution. So you have to be correct. So if you do plugin on a subspace of model, it's going to fail for some models that aren't in that subclass. So it is regular, but it's not a good estimator.
Wait, are you telling me that the model-based estimator is not good? Or
it depends on what class you're doing the model-based. Like among which space are you doing your MLE? If you're doing it in the small class of model, then it is regular, but it might not converge in distribution at a root and rate for models that are in the big class of model.
Sure, but do we care about the models in the big class of model? We don't, right?
No, so the definition is that it has to be regular for that like bigger class of model.
Why is that the definition?
Because this is kind of the philosophy is in the model-free methods, you start from a state of a class of value functions. What is like you still need a data generating process. So which data generating process do you pick? You pick all the models that fit into that value function.
Okay.
I think there is definitely this is something that we have had very long conversation with Dan.
Okay.
I think there's multiple way of writing the result, and some are more or less kind of like elegant. But what we're saying is that a model is lower bounded, like the performance of any estimator is lower bounded by the performance of plugin on the biggest class of model with which it's good and regular. So if you pick LSTD is like regular with everything, good with everything. So it's going to have performance lower bounded by plugin on the very large class of model. Like, I think in some sense what this is capturing is if you write your theorem, like you come up with a new algorithm and you write it as like your guarantees on that theorem looks like for all V in V, like in big V, we have some like guarantees. Then you are lower bounded by the performance of like on the big model class.
Okay, maybe I take a very careful look after the talk because I'm not sure I follow any more of the big and the small model class and all that. I thought that, yeah, maybe.
I will say I do think I do think it is a little hard to like gauge kind of like the strength of the main theorem without kind of like understanding how the like regularity condition comes in like kind of like quantitatively to like the sort of, you know, to the like 1 over n kind of part. But I do think it's pretty cool. Yeah.
I think the regularity is really just if you don't have that,
Yeah.
you can always have one estimator that's going to be kind of like decent.
Yeah.
everywhere,
No,
and then-
I know you have to have like some kind of regularity condition, but like, I think like the details of like how strong is the regularity condition and like, yeah, like how does this influence like the statement of the end result like quantitatively is like important. But actually, this reminds me of another question I wanted to ask, which is if people want to like read the proof and try to is that in the version of the paper that's online right now, or do we need to wait for the new version?
you have to wait for the new version. The former
fast.
version was like mainly the example, because that's what we thought as being like the core. But then people were kind of like, rightfully so, be like, okay, we need a bit more. And so the new version will have the rest. What I'm going to say for regularity is, like, I'm talking a lot about like all those, like in the case of value function, but really what we're doing is this in a special case.
For sure.
And like people who have been thinking about that for a long time in stats have come up with like regularity is the right thing to enforce to be able to like,
I think that like it's the right way to enforce that the math works.
I agree.
I'm sorry, what did you say?
I think it's the right way to enforce that the math works.
Yeah.
That's my impression.
But
it's true. It captures some regularity about algorithms and whatnot, but that doesn't necessarily mean that this is the right thing to do. But
okay, I agree with
that. But my question was rather elementary. It was more like, I just want to understand, like, I have this model-based approach, and like, why can't I call it model-free? And so now you are telling me that I can't, like the model, like that builds the model and then estimates the value function. Why doesn't it fit the definition of yours? And there you were telling me that, well, because
I'm not sure I understand what your model-based method is. I think my model.
I guess like in the examples that we have, this is how it works. We have a model class, the model class of interest.
Yeah.
And then we conclude that the value functions for these models are of special form. So we will have a value function class. At this stage, I can stop. I don't loop back to the even bigger model class now. And I just say, well, I had the model class of interest. So I'm going to build this value function estimator that uses maximum likelihood to pick the best model given the data, then solves the model, returns the value function. And now I go back to your definition. I just want to check whether this method qualifies as model free or not. Because I don't care about like how we call it or whatnot, but I just want to see whether the definition is going to not allow me to do this, and which part of the definition is not allowing me to do this.
Isn't it that it like doesn't converge asymptotically necessarily for models in like the bigger class induced by the value functions?
Yeah. So I think the thing is the model-based thing you suggest does not work for all the value functions. It works for all the models in your class.
That's right. Yeah.
And that's why I don't want to call
so at that stage, I would say, like, why do I care?
Because, okay, that's a good question. You care because in practice you don't necessarily like. I think this is kind of like the Tetris. That's why I was trying to add the Tetris. In practice, you don't know that it is like
Tetris
decomposable. Like it's Tetris, and you make those features, and then you run LSTD.
Right.
And it's like.
So it's like the under specification or misspecification issue with the model class.
It's like
that how sensitive you are. Like it's not only that. Like, if this was a clean situation where the model class is surely not misspecified.
Exactly. If you know exactly what the model is, then why would you do anything else than something that's like works for the class of model? You don't care about working for all class.
Right.
This is more saying if you pick something that's going to be broadly good for any value function, like if you pick an off-the-shelf algorithm that works no matter what the underlying model is, you're going to suffer that cost. You need that specification to the class of model to be statistically efficient.
It is more aligned with the thinking that once you pick your bias for the value functions, that's what you're married to. You believe in that. That's really what you care about. And if that specification is correct, then you expect your method to work well.
Yeah.
And you're pointing out that with this mindset, you somehow run into trouble. But in a weird way, because then we have to go back to like that. Oh, if you had a smaller model class that is part of the bigger model class that would support this value function class, and your model would actually be there, then like there would be this performance gap, which can be very, very large.
Yeah,
which
I think
is
this is
maybe saying that like the model 3, yeah, like, well, it's just limited in what it can capture, and
yeah. I think this is like the overall idea is that modeling a simple value function is actually not necessarily modeling a simple model, underlying model.
For sure.
And so when you go to this problem like Tetris and you do like, okay, I'm going to do a very simple value function, this probably is like modeling nicely the transition. This is not the case.
Yeah.
And
But the really
idea we're
important
trying
thing there is like the fact that like picking a simple value function doesn't necessarily mean a simple model. Like that's pretty immediate. Like the cool part is that like it doesn't necessarily mean a simple model, and you are paying for that fact statistically,
Yeah,
even
exactly.
potentially on models that are simple.
Yeah.
Yeah.
Exactly.
yeah.
And so
Yeah.
I think this is something like like maybe if, instead of saying like, oh, I know that my value function is like decomposable, is like, I know I have some symmetry in the problem. Should I try and model, like come up with a class of model that encode those symmetries, or can I just come up with a class of value function that encode that symmetries? Is not the same.
Yeah.
Yeah.
You have to be in the tabular case.
Exactly.
Right.
And for regularity, I don't know, I've been playing a bit around with it. I'm not sure it's the right definition. It is kind of hard to come up with estimators that are not regular. And it's really not regular at a lot of points. Like this is usually like you have a regularization that does not decay with.
I think artificially I can do that, but I wouldn't
Right.
agree
No,
that
artificially we can. It's very easy to do, but like in practice,
yeah.
you really need to either like literally
Right.
test for some stuff,
You know,
or have infinite
yeah.
regularization, like infinite priors or something like that. It's actually hard to do in practice.
And it's actually common wisdom that you probably better off with a smooth kind of like method than a method that abruptly changes what it thinks about what should happen. The only question is like whether such abrupt changes would actually happen like as a side effect of other things, but that almost indeed never happens.
And I mean, I think as you said also, Dylan, is like, you know, the theorem is actually really tautological once you have the definition. Like it's I think the core part for me is having those examples that shows that working in the bigger class of model actually pays a cost.
Yeah, no, I think it's yeah. Just to be clear, I think it's like quite cool. Yeah,
yeah. But I think like the first time we submitted it was like kind of just the example showing like, see, you pay the cost, and people were like, and rightfully so, I think, right? I'm not complaining about it, but it's like we need to like have some theorem that we can use, and I think like regularity was one way of having kind of like a clean theorem that we can explain, and then put the examples.
Yeah, and you can imagine doing like mini like follow-ups and things and trying to get an even tighter understanding and stuff, right?
Yeah, of
but
course.
I think it's like a good starting point. Yeah.
Awesome.
Thanks a lot.
I need to run now. But yeah, great talk. I really enjoyed it.
Thanks a lot.
Same here.
Cool.
See you.
Thanks.